Let's try some really simple examples of assigning oxidation states. If you ever see an element by himself, like silver here, the oxidation state is always 0, every single time. Now you look at F2 here, and there are 2 of them, but it's still an element all by his lonesome, so his oxidation state is still 0. Very, very simple. Here, if you have a charge like you do with Mg2+, whatever the charge is, as long as it's a single ion by itself, your oxidation state is just the charge. So here magnesium would be +2. So these are really simple examples, but we won't always have an element by itself. Sometimes we see a compound. Like here we have barium chloride. Now barium is an alkaline earth metal, so his charge is always the same thing from the periodic table. So his oxidation state is going to be the same thing. He is going to be +2. Chlorine from the periodic table is going to be -1. So for ionic compounds, if you have an alkali or alkaline earth metal and a non-metal, you can very easily assign their oxidation states just by looking at the periodic table. Now our next example with FeBr3, iron bromide. Fe, that's a transition metal, so we can't predict his charge from the periodic table. That's okay, we can use the bromine atom to figure it out. So I always like to make what I call a T-chart. So I write out my compound and I make a T. And I ask myself how many of each element I have. I have 3 bromines and I have 1 iron. Bromine I can get from the periodic table. He is -1. -1 times 3, total negative charge of -3. Now notice there's no charge on this. It's a neutral compound, which means all of my charges have to add up to 0. So I have a -3, I must have a +3 to balance it out. And since there's only 1 iron, his oxidation state must be +3. So here I'm going to look at the individual charges on each atom. So for iron it's going to be +3, and for bromine it's going to be -1. So now I figured out their oxidation states. N2O5 is another tricky example because if we just look at the periodic table, it looks like they both have negative oxidation states, and that doesn't make sense because in a neutral compound they have to add up to 0. So for these we have to do something very, very similar to what we just did for iron bromide. So I'm going to do the same thing. I'm going to make my T chart. I'm going to have an N2O5, make a little T. I have 2 nitrogens. I have 5 oxygens. The basic rule is that the more electronegative atom gets to have the charge he wants from the periodic table, while the other atom has to be whatever makes the charges cancel out. Good rule of thumb is the element on the right always gets priority. He always gets to do what he wants. So here we have oxygen. His charge from the periodic table is -2. So the total negative charge is -10. We have a neutral compound, which means these have to add up to 0. There's no charge here, so they have to add up to 0. So if I have a -10, I must have a +10 over here. Since there's 2 nitrogens, each one of them must have an oxidation state of +5. Not what nitrogen wants to be, but what he has to be to make all of this balance out. So overall, my nitrogen oxidation state is +5. My oxygen oxidation state is -2. So in compounds, sometimes it takes a little more work, and we can even look at a couple more complicated examples. Let's look at 2 more complicated examples here. So here with the phosphate ion, we have a polyatomic ion. Not really that much harder, except that now our charges don't cancel out to 0. They have to leave a -3 because the overall charge is -3. So I do the same thing I did before. I make my little T chart, separate. I have 1 phosphorus. I have 4 oxygens. Once again, the element on the right gets priority, gets to be what he wants, so oxygen is -2. -2 times 4 gives me a total negative charge of -8. Now phosphorus doesn't cancel that completely. I have a total charge of -3 on the whole phosphate, so when I add up all the positive and negative charges, they have to add up to -3. So phosphorus over here, what -8 will give me -3? Answer is plus 5. So there's only one phosphorus. His charge must be positive 5. So I can see phosphorus has a charge of plus 5, not what he wants from the periodic table, but what he has to be to make it work out. Oxygen has a charge of -2, or an oxidation state of -2, and overall we have a leftover -3 charge as indicated in my polyatomic ion. Finally, sometimes you'll see compounds where you have more than 2 elements, like in the case here of iron sulfate. So let's look at that example. Oops. We have Fe2SO4 3. For me, I think the easiest thing to do is do it in 2 stages. First, we can look at it and say, okay, I need to separate iron and sulfate. So I'm going to do a little bit of a T-chart here. Now I'm going to have to look at sulfate closer later, but this will get me started. I'm going to do the same thing I've been doing. I have 3 sulfates. I have 2 irons. Sulfate, the polyatomic ion, has a charge of -2. So here I have -6. It's a neutral compound, so these add up to 0. So over here, iron total must be +6, but there's 2 of them, so each one must be +3. So iron's oxidation state is +3. Now that I've done this, I'm going to go back to sulfate and take a closer look at that guy, because I still need to figure out the sulfur and oxygen individually. So I'm going to keep in mind iron was +3. And now I'm just going to look at this sulfate, which I know has a total charge of -2. I don't care that there are 3 of them in the compound. I use that information to figure out what iron's charge was, but it's not going to affect sulfur or oxygen. So now I'm just going to do another T-chart. Make a little chart, same thing. I have 4 oxygens, each has a charge of -2, 1 sulfur. I can see that I have a total charge here of -2, so that's what my charges have to add up to. Oxygen gives me -8. Sulfur must be +6. 6 minus 8 gives me -2, so sulfur must be +6. So here I see iron is +3, sulfur +6, and oxygen -2. So even when I have 3 elements, I can just use an extra step in order to figure out those oxidation states.